Hello and welcome to G Fun Facts Online, the show where we explore the most incredible science from our universe and beyond. What if I told you that some of the most breathtaking images of our cosmos, pictures of entire galaxies being born, aren't taken by a telescope? What if they weren't captured with lenses and light at all, but were instead born inside the silicon heart of a computer? Today, we're diving into the revolutionary world of computational astrophysics, where scientists don't just observe the universe, they build it from scratch. For centuries, astronomy stood on two great pillars: observation, which is gathering light from distant stars and galaxies, and theory, the mathematical rules that explain why celestial objects behave the way they do. But there's a problem. Many of the most fascinating events in the cosmos are impossible to watch in real time. Think about it. We can't watch a single galaxy form over 14 billion years. We can't peek inside an exploding star to see what's happening. And we certainly can't create a black hole in a lab to study it up close. This is where computational astrophysics rises as the third pillar of astronomy. It's a virtual laboratory where the entire universe, or at least a chunk of it, can be simulated. It allows scientists to model cosmic events that are too slow, too big, or too dangerous to study any other way. So, how on earth do you build a universe in a box? Well, you can think of it like baking the most complex cake imaginable, using a recipe that's 13.8 billion years old. The process doesn't start with how the universe looks now. It starts with the absolute beginning, with the faint echo of the universe's birth, the cosmic microwave background. This is relic radiation from when the universe was just a baby, about 400,000 years old. It gives scientists a map of the early cosmos when it was a hot, dense, and almost perfectly smooth sea of matter and energy. This map is the starting point for their digital box. Into this box, they add the fundamental ingredients of our cosmos. And this is where it gets really interesting. The familiar atomic matter that makes up you, me, the stars, and the planets, that's only about 5% of the total cosmic inventory. The other 95% is made of two completely mysterious components: dark matter and dark energy. We can't see them, we can't touch them, but we know they're there because we can see their gravitational effects on everything else. So any realistic simulation has to include this massive, invisible dark sector. Once the ingredients are in the box, scientists program in the rules. These are the fundamental laws of physics we know and trust: gravity, gas dynamics, the processes of how stars form and how black holes grow. With the stage set and the rules in place, they hit go, and the supercomputer takes over. It meticulously calculates the interactions between trillions upon trillions of virtual particles, simulating billions of years of cosmic evolution in just a few weeks or months. Now, running these cosmic simulations isn't something you can do on your home computer. They are so computationally expensive that they can only be run on the most powerful machines on the planet. We are now officially in the era of exascale computing. This means supercomputers can perform over a quintillion. That's a 1 with 18 zeros after it. Calculations per second. A billion calculations every single second. Leading this charge is a machine named Frontier, located at the Oak Ridge National Laboratory. It's the world's first publicly acknowledged exascale supercomputer, a true titan of computation. And this incredible hardware has given rise to a new generation of landmark simulation projects. You can think of them as the masterpieces of computational art and science. For example, there's the IllustrisTNG project. This is a suite of simulations that model the formation of thousands of galaxies in absolutely stunning detail. It tracks how dark matter, gas, stars, and supermassive black holes all evolve together to create the kind of realistic, spiral and elliptical galaxies we see through our telescopes. The project's data, which is over a petabyte in size, is even publicly available for any astronomer in the world to explore. Then there's the MillenniumTNG simulation, which tracks hundreds of millions of galaxies in a simulated volume of space over 2,400 million light-years across. Its main goal is to conduct precision tests of our standard model of cosmology, the theory that explains how our universe grew from the Big Bang. But perhaps the most stunning achievement came in late 2023. Researchers used the Frontier supercomputer to run the largest and most detailed astrophysical simulation of the universe ever conducted. For the first time, they could model both the normal, atomic matter and the invisible dark matter at a scale that perfectly matches the vast surveys being done by our best telescopes. This simulation didn't just include gravity. It contained what scientists called the astrophysical kitchen sink, everything from hot gas to star formation and black hole growth, creating the most complete virtual cosmos to date. Of course, the direct output of a supercomputer simulation is not a beautiful picture. It's a colossal flood of numbers. We're talking terabytes or even petabytes of data representing the position, velocity, and temperature of every single particle in the virtual universe at thousands of different points in time. Turning this numerical avalanche into the breathtaking vistas we see online is a crucial step known as scientific visualization. This process is both an art and a science. Astrophysicists use sophisticated software tools, some of which are even used in the Hollywood film industry, to translate that raw data into images and animations. They might assign color and brightness to represent the density or temperature of gas, or trace the paths of individual stars to reveal the slow, graceful formation of a galactic disk. The goal is to create a visual that is not only beautiful, but scientifically accurate and informative, allowing the human brain to intuitively grasp what all that data is telling us. And these digital universes are so much more than just pretty pictures. They are indispensable tools for tackling the biggest mysteries in the cosmos. By comparing their virtual universe to the real one observed by telescopes like the James Webb Space Telescope, scientists can test and refine their theories. For instance, simulations clearly reveal the universe's large-scale structure, showing how galaxies aren't just scattered randomly through space. Instead, they are arranged in a vast filamentary network known as the cosmic web, surrounding immense, empty voids. Because we can't see dark matter and dark energy, simulations are one of our best tools for figuring out what they are. Scientists can run simulations with different theoretical properties for these dark components. The model that produces a virtual universe most closely matching our real one is our best bet for being correct. And, of course, they allow us to witness galaxy formation. We can finally watch how the magnificent spiral and elliptical galaxies we see today slowly emerged from the smooth, primordial soup of the early universe. We can even recreate the formation of our own Milky Way galaxy and see if it matches what we observe. The future of this incredible field is accelerating. The continued push into the exascale era means future supercomputers will be even more powerful, enabling simulations with even finer detail. At the same time, the AI revolution is providing new tools. Machine learning algorithms are becoming essential for sifting through the petabytes of simulation data to find subtle patterns that a human eye might miss. This creates a powerful, iterative cycle of discovery. Supercomputers make predictions. New telescopes test those predictions with real observations. And that new data is then fed back to create even more accurate and sophisticated simulations. In our grand quest to understand our cosmic origins, supercomputers have become our indispensable time machines and our most versatile laboratories. They empower us to photograph the unseeable, watch the impossible unfold, and piece together the epic story of our universe, one calculation at a time. Thank you for tuning in to G Fun Facts Online. Join us next time for another journey into the wonders of science.